Aero Engineering Thermodynamics. Limitation of the first law of thermodynamics. It does not say anything about the direction of flow of heat. It does not say anything whether the process is a spontaneous process or not. The reverse process is not possible. In actual practice, the heat doesn't be converted completely into work. Introduction to the second law. It is common experience that a cup of hot coffee left in a cooler room eventually cools off. This process satisfies the first law of thermodynamics, since the amount of energy lost by the coffee is equal to the amount gained by the surrounding air. A cup of hot coffee does not get hotter in a cooler room. Limitations of the first law of thermodynamics. Now let us consider the reverse process, the hot coffee getting even hotter in a cooler room as a result of heat transfer from the room air. This process never takes place. Yet, doing so would not violate the first law as long as the amount of energy lost by the air is equal to the amount gained by the coffee. Limitations of the first law of thermodynamics. The first law places no restriction on the direction of a process, but satisfying the first law does not ensure that the process can actually occur. This inadequacy of the first law to identify whether a process can take place is remedied by introducing another general principle, the second law of thermodynamics. Transferring heat to a wire will not generate electricity is another familiar example. Consider the heating of a room by the passage of electric current through a resistor. Again, the first law dictates that the amount of electric energy supplied to the resistance wires be equal to the amount of energy transferred to the room air as heat. Now let us attempt to reverse this process. It will come as no surprise that transferring some heat to the wires does not cause an equivalent amount of electric energy to be generated in the wires. Finally, consider the paddle wheel mechanism that is operated by the fall of a mass. The paddle wheel rotates as the mass falls and stirs a fluid within an insulated container. As a result, the potential energy of the mass decreases, and the internal energy of the fluid increases in accordance with the conservation of energy principle. However, the reverse process, raising the mass by transferring heat from the fluid to the paddle wheel, does not occur in nature, although doing so would not violate the first law of thermodynamics. Second law of thermodynamics. The use of the second law of thermodynamics is not limited to identifying the direction of processes, however. The second law also asserts that energy has quality as well as quantity. The first law is concerned with the quantity of energy and the transformations of energy from one form to another with no regard to its quality. Second law of thermodynamics. Preserving the quality of energy is a major concern to engineers, and the second law provides the necessary means to determine the quality as well as the degree of degradation of energy during a process. The second law of thermodynamics is also used in determining the theoretical limits for the performance of commonly used engineering systems, such as heat engines and refrigerators, as well as predicting the degree of completion of chemical reactions. Thermal energy reservoirs. It is very convenient to have a hypothetical body with a relatively large thermal energy capacity, mass x specific heat that can supply or absorb finite amounts of heat without undergoing any change in temperature. Such a body is called a thermal energy reservoir, or just a reservoir. Bodies with relatively large thermal masses can be modeled as thermal energy reservoirs. In practice, large bodies of water such as oceans, lakes, and rivers as well as the atmospheric air can be modeled accurately as thermal energy reservoirs because of their large thermal energy storage capabilities for thermal masses. The atmosphere, for example, does not warm up as a result of heat losses from residential buildings in winter. Likewise, megajoules of waste energy dumped in large rivers by power plants do not cause any significant change in water temperature. The air in a room, for example, can be treated as a reservoir in the analysis of the heat dissipation from a TV set in the room, since the amount of heat transfer from the TV set to the room air is not large enough to have a noticeable effect on the room air temperature. A reservoir that supplies energy in the form of heat is called a source, and one that absorbs energy in the form of heat is called a sink. Thermal energy reservoirs are often referred to as heat reservoirs since they supply or absorb energy in the form of heat. Work can easily be converted to other forms of energy, but converting other forms of energy to work is not that easy. Work can always be converted to heat directly and completely, but the reverse is not true. The mechanical work done by the shaft, for example, is first converted to the internal energy of the water. This energy may then leave the water as heat. We know from experience that any attempt to reverse this process will fail. That is, transferring heat to the water does not cause the shaft to rotate. Heat engines' work can be converted to heat directly and completely, but converting heat to work requires the use of some special devices. These devices are called heat engines. Everyday examples of heat engines include the thermal power station, internal combustion engine. Part of the heat received by a heat engine is converted to work, while the rest is rejected to a sink. Heat engines differ considerably from one another, but all can be characterized by the following. 1. They receive heat from a high-temperature source, solar energy, oil furnace, nuclear reactor, etc. 2. They convert part of this heat to work, usually in the form of a rotating shaft. 3. They reject the remaining waste heat to a low-temperature sink, the atmosphere, rivers, etc. 4. They operate on a cycle. Part of the heat received by a heat engine is converted to work, while the rest is rejected to a sink. Heat engines and other cyclic devices usually involve a fluid to and from which heat is transferred while undergoing the cycle. This fluid is called the working fluid. The term heat engine is often used in a broader sense to include work-producing devices that do not operate in a thermodynamic cycle. Engines that involve internal combustion such as gas turbines and car engines fall into this category. These devices operate in the mechanical cycle but not in a thermodynamic cycle, since the working fluid, the combustion gases, does not undergo a complete cycle. Instead of being cooled to the initial temperature, the exhaust gases are purged and replaced by fresh air and fuel mixture at the end of the cycle. The work-producing device that best fits into the definition of a heat engine is the steam power plant, which is an external combustion engine. That is, combustion takes place outside the engine, and the thermal energy released during this process is transferred to the steam as heat. The schematic of a basic steam power plant. This is a rather simplified diagram, and the discussion of actual steam power plants is given in later chapters. The various quantities shown on this figure are as follows. Kin equals amount of heat supplied to steam in boiler from a high temperature source furnace. Out equals amount of heat rejected from steam in condenser to a low temperature sink, the atmosphere, the river, etc. Watt equals amount of work delivered by steam as it expands in turbine. Wind equals amount of work required to compress water to boiler pressure. Schematic of a steam power plant. A portion of the work output of a heat engine is consumed internally to maintain continuous operation. The net work output of this power plant is simply the difference between the total work output of the plant and the total work input. Thermal efficiency, the fraction of the heat input that is converted to net work output, is a measure of the performance of a heat engine and is called the thermal efficiency. For heat engines, the desired output is the net work output, and the required input is the amount of heat supplied to the working fluid.